Right above you tonight, past the roof and the thin skin of air, is a sky that got its name from a man who thought the whole idea was stupid. A radio studio in London, 1949, and a phrase picked to sound ridiculous: one big bang. A Belgian priest, 2 years before Hubble, writing 457 words saying the beginning happened before there was any time for it to happen in. A universe colder and emptier and more silent than anything since. One field filling everything, holding still, holding every star and every ocean and every hand that will ever exist. And then that field falling, everywhere at once, no centre, no sound, and everything pouring out of it. Here is what nobody tells you. The fireball everyone calls the beginning of the universe is not a beginning. It is the ending of something else, and we have measured it. By the end of tonight you will know why the question everybody asks, how did nothing start, may not have the shape you gave it. Get comfortable. If you would rather find out your question was built wrong than be handed a comfortable answer, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, the word beginning will not mean what it meant when you lay down. Now, let's gently drift into this. On the 28th of March, 1949, a man sat down in a London studio with a typed script in his hands, leaned toward a microphone, and gave a name to something he was certain was nonsense. His name was Fred Hoyle. He was one of the most gifted astronomers of his generation, and he was there that evening to talk about the universe on the BBC's third programme, which was the sort of radio you listened to in an armchair with the lights low. Hoyle believed, and would believe for the rest of his life, that the universe had no beginning at all. He was one of the three architects of the steady-state theory, in which the cosmos simply is, and always has been, and always will be, expanding forever while new matter quietly appears in the gaps to keep the density from ever thinning out. It is a beautiful idea. It is also, as it turns out, wrong. But on that evening in 1949, nobody could prove it either way, and Hoyle had the microphone. So he did what any good broadcaster does when he wants an audience to side with him. He described the competing idea in the least flattering terms he could manage. The other view, he explained, was the hypothesis that all the matter of the universe was created in one big bang at a particular time in the remote past. And by the end of the talk he had made his position perfectly clear. A creation process of that sort, he said, was irrational, and it lay outside science altogether. Less than 2 weeks later, the full text of the talk was reprinted in The Listener, the BBC's magazine, which sold in very large numbers. And that is how the phrase got out of the studio and into the language, where it has stayed for 77 years. Here is what I want you to sit with before we go any further tonight. The picture in your head of how the universe began, the one you have carried since you were a child, was drawn for you by a man who was trying to make it sound stupid. And it worked. It worked so completely that his insult is now the official name of the winning theory, printed in textbooks, taught in schools, spoken by people who have never heard of him. The theory he was attacking went on to be confirmed by 5 separate lines of evidence and to become one of the great achievements of the human mind. And it is still walking around wearing the name he gave it as a joke. But here is what almost nobody stops to notice. That name is not a neutral label. It is a description. It is 3 specific claims about what happened, packed into 2 short words, and every single one of them is wrong. Take the first word. A bang is a sound. Sound is a pressure wave, and a pressure wave needs something to travel through, some medium that can be compressed and released. In the early universe there was no outside air because there was no outside and no air. There was no room around the event for a noise to cross. Nothing banged because there was nothing for a bang to happen in. Whatever occurred was, as far as any observer is concerned, absolutely silent. Take the second idea, the one that arrives with the word even when the word does not say it. An explosion is a thing that happens at a location. There is a centre where the charge sits, and material flies outward from that centre into surrounding space that was already there and stays there. That is how every explosion you have ever seen or heard of works, from a firework to a supernova. And that is exactly what did not happen. The early universe was not a dense object sitting somewhere in a large empty room. There was no room. Space itself was part of what was expanding, which means there is no centre to point at, because every point is equally the centre, which is the same as saying there is no centre at all. The event did not happen over there. It happened here, in the volume of air currently occupying the space above your bed, and it happened simultaneously in every other volume of space that exists, and it is still happening because the expansion never stopped. And take the third piece, the one hidden in the phrase at a particular time in the remote past. That sounds harmless. It sounds like a date on a calendar. But a date is a position in a sequence, and a sequence needs a before and an after, and whether there was a before is exactly the thing nobody can currently say. Hoyle's phrase quietly assumes an answer to the deepest question in the subject, and it assumes it in the space of 4 words, and we have all been repeating it ever since without noticing that we were smuggling something in. So we have a name that is wrong about sound, wrong about location, and possibly wrong about time. It is a remarkable piece of work for 2 syllables. Hoyle himself said later that he had not meant it as a sneer, that he was simply reaching for a vivid image for a general audience. That may be partly true. Broadcasters do reach for vivid images. But the surrounding text of that 1949 talk is not the text of a man being generous, and he spent the next half-century arguing that the theory was wrong, and he never conceded, not even at the end when the evidence had closed off every escape. Both things can be true. He may not have intended a knife. He certainly handed one over. And the reason all of this matters, the reason I'm spending the opening of the night on a word rather than on the universe, is that the picture blocks the explanation. As long as you are imagining a bang, you cannot see the thing that actually happened. You're looking for a location and there isn't one. You're listening for a sound and there is nothing to hear. You're picturing a first moment and the physics may not have one. Every time somebody tries to explain the true state of affairs to a general audience, they have to spend the first 10 minutes prying the 1949 picture out of the way, and usually they run out of time before they get to the interesting part. Tonight we have time. We're going to get to the interesting part, because there is something considerably stranger waiting underneath all this than a mistaken name. It is not simply that the Big Bang was not a bang. It is that the Big Bang, on the best account physics currently has, was not the beginning of anything. It was the end of something else. The fireball everybody pictures as the origin of the universe is, in the leading theory, an aftermath. It is what was left over when a completely different process finished running, dumped everything it had, and stopped. That process did not happen at the beginning. It happened before what we call the beginning. It is the reason your sky is smooth, the reason space is flat, the reason there are galaxies at all rather than a featureless fog, and the reason you exist in a form complicated enough to be lying there listening to this. It ran for an almost unimaginably short time, and then it wiped out nearly every trace of whatever came before it, deliberately and thoroughly, as a side effect of what it was doing. And here is the part that I find genuinely difficult to get used to, even now. We can measure it, not guess at it, not model it, not tell an appealing story about it. Measure it. There is a number, written down in a paper, 4 decimal places long, that is a direct measurement of a property of that process, and we know it more precisely than we know the mass of the Earth was known a century ago. We will get to that number tonight. I am going to make you wait for it, because the waiting is part of understanding what it is. But first we have to go back a little further than 1949, to a man who wrote the theory down before anybody had the observations to support it, who was told by Albert Einstein that his physics was abominable, and who said something about the beginning of the universe that almost nobody who repeats his idea today has ever read. 2 years before the discovery that made Edwin Hubble famous, a Belgian priest in a Roman collar sat down with Einstein's field equations and solved them for a universe that was getting bigger. His name was Georges Lemaitre. He was a Catholic priest, ordained in 1923, and he was also a properly trained physicist who had studied at Cambridge under Arthur Eddington, and then at Harvard and at the Massachusetts Institute of Technology. In 1927 he published a paper showing that Einstein's own theory of gravity, taken seriously and applied to the universe as a whole, does not describe a static cosmos. It describes an expanding one, and he did not stop at the mathematics. He went to the astronomical data that existed at the time, worked out how fast the expansion was going, and produced a number for the relationship between how far away a galaxy is and how fast it is receding. He published it in the Annals of the Scientific Society of Brussels. If you have never heard of that journal, neither had most physicists in 1927. Outside Belgium it was very nearly invisible. He had written down one of the great results of the century and put it somewhere almost nobody would look. He was not even the first. In 1922, a Russian mathematician named Alexander Friedmann had found essentially the same family of expanding solutions and published them properly in a German journal, where Einstein read them and responded in print that Friedman had made an arithmetic error. Einstein was wrong. The error was his own, and he retracted the objection the following year, but the damage was done and the work sank. Friedman treated the solutions as mathematics rather than as a description of the actual sky, and he never got the chance to change his mind about that, because he died of typhoid in 1925 at the age of 37. And underneath both of them sits a third man who almost never gets named at all. Between 1912 and 1917, an American astronomer called Vesto Slipher, working at the Lowell Observatory in Arizona, painstakingly measured the spectra of spiral nebulae and found that almost all of them were shifted toward the red end. Those measurements are the raw evidence. Lemaitre used them, Hubble used them, and when the story gets told, it is usually told as though the universe was discovered to be expanding in 1929 by a man with a very large telescope, rather than assembled slowly out of somebody else's spectra by a priest with a pencil. In October of 1927, Lemaitre went to Brussels for the 5th Solvay Conference. If you have ever seen the photograph, you have seen this conference. 29 people arranged in 3 rows, 17 of whom either had won or would win the Nobel Prize, with Einstein in the centre of the front row looking directly at the camera. It is the most famous photograph in the history of physics. Lemaitre, who was 33, found Einstein during the meeting and told him about the expanding solution. Einstein's reply has become one of the most quoted sentences in the field. "Your calculations are correct," he said, "but your physics is abominable." It is worth being precise about what he meant, because the popular version flattens it into a simple story about a genius refusing to accept a new idea. And that is not quite what happened. Einstein was not saying that expansion was mathematically forbidden. He knew perfectly well that the equations permitted it, which is why he had inserted a term into them years earlier, specifically to hold the universe still. His objection was partly technical, concerning how Lemaitre was handling that term, and partly a conviction, deeply held and widely shared, that a universe with a history was simply not a physically reasonable thing to propose. He also told Lemaitre that Friedman had got there first, which Lemaitre had not known. 4 years later, Einstein changed his mind entirely and said so in public. But in 1927, the most celebrated physicist alive looked at a correct description of the real universe and told the man holding it that his instincts were abominable. There is a small detail about that Belgian paper that I love, because it says something about the kind of man Lemaitre was. In 1931, once the result finally mattered, the paper was translated into English for the monthly notices of the Royal Astronomical Society, and in the English version, the paragraphs containing his estimate of the expansion rate are simply missing. For decades, this was treated as suspicious, as though somebody had quietly removed a priest's claim to priority. When historians eventually went looking, they found the answer in the correspondence. Lemaitre had deleted them himself. He thought Hubble's newer measurements were better than his own, and saw no reason to reprint numbers he considered superseded. He gave away the credit for one of the most famous constants in science because he did not think his version of it was good enough. His old supervisor, meanwhile, was having none of any of it. Arthur Eddington, who had taught Lemaitre at Cambridge, and who was one of the most influential astronomers alive, wrote publicly that the notion of a beginning of the present order of nature was philosophically repugnant to him. That is a strong phrase from a careful man, and it is worth noticing what kind of objection it is, because it is not an objection about data at all. It is a statement about taste. Two of the most powerful figures in the field looked at the same equations and rejected the answer, because it felt wrong. Lemaitre's 1931 note in Nature was written, in part, as a direct reply to that remark. Now here is where it becomes interesting for our purposes tonight, because Lemaitre did not stop at expansion. If space is getting bigger, then running the film backwards means it used to be smaller and denser, and if you keep running it backwards you arrive somewhere. In 1931 he published a note in the journal Nature, dated the 9th of May, under the title The Beginning of the World from the Point of View of Quantum Theory. It is 457 words long. That is shorter than the last 5 minutes of what you have been listening to. In it, he argued that as you run the expansion backwards you find fewer and fewer quanta, fewer and fewer separate units of energy, until at last the entire energy of the universe is packed into a few, or even into a single one. He called it the primeval atom. Everything that exists on this picture is the debris of the disintegration of one enormous quantum. Later he described the galaxies as embers from a firework, and he is remembered for calling that moment a day without yesterday, a phrase that has followed him for 90 years. Hold on to that phrase, a day without yesterday. It sounds like poetry, and tonight it sounds like poetry, and there is nothing wrong with hearing it that way for the moment. We are going to come back to it much later, and when we do, you're going to hear it as something else entirely. Because there is a sentence in that 457-word note that is not poetry at all, and it is the sentence this entire video is a footnote to. Lemaitre wrote that if the world began with a single quantum, then the notions of space and time would altogether fail to have any meaning at the beginning. They would only begin to have a sensible meaning, he said, once the original quantum had divided into a sufficient number of quanta, and then he wrote the line, "If this suggestion is correct, the beginning of the world happened a little before the beginning of space and time. Read that again slowly." The man who invented the beginning of the universe wrote, in the paper where he invented it, that the beginning happened before there was any time for it to happen in. He was not claiming to have found the first moment. He was explicitly saying that the concept of a first moment does not survive the trip. He put the warning inside the theory, in print, in 1931, and it has been sitting there ever since while the rest of us argue about what came before. He was equally careful about the other thing everybody wants to do with his idea. Lemaitre was a priest, and the temptation to read the primeval atom as a scientific proof of the opening line of Genesis was immediate and enormous. He refused it consistently for the rest of his life. At the Solvay Conference of 1958, he wrote that the hypothesis remains entirely outside any metaphysical or religious question, that it leaves the materialist free to deny any transcendental being, and that for the believer it removes any attempt at familiarity with God. It is consonant, he said, with Isaiah speaking of a hidden God, hidden even in the beginning of creation. He meant it. In November of 1951, Pope Pius XII gave an address to the Pontifical Academy of Sciences in which he used the primeval atom to argue for creation in the theological sense. Lemaitre was disturbed by it. The theory was not even accepted yet, and he objected to the conflation of a beginning with a creation, which are two very different claims. He appears to have worked through the Pope's scientific advisor to have the argument quietly dropped, and it did not appear in the follow-up address the next year. Years later, he summed up his position in one line. The attitude of the Pope, he said, is situated in the terrain which is proper to him, and it has no relationship to Eddington's theories or to mine. That, incidentally, is the answer to a claim you will still hear regularly, which is that the Big Bang was invented by a priest and is therefore religion in a lab coat. The theory was named as an insult by an atheist who thought it was mystical nonsense, and it was derived by a priest who spent decades refusing to let anyone use it as theology. The truth is almost precisely the inverse of the accusation, and in any case the theory's standing does not rest on either man. It rests on measurements, which is where we go next. Because for 30 years after Lemaitre published, nobody could settle the argument. Two beautiful theories, one with a beginning and one without, and no way to choose. What finally decided it was not a telescope pointed at the beginning. It was a group of men in Cambridge counting faint radio sources, and it ended in one of the most uncomfortable rooms in the history of science. In a field outside Cambridge in the 1950s, a group of men were pointing wire aerials at the sky and writing down how many faint radio sources they could hear, and that piece of bookkeeping is what killed the steady-state universe. It is not the sort of thing you would expect to settle the biggest question in cosmology. Nobody photographed the beginning. Nobody detected an echo, not yet. They counted. And the reason counting works is a piece of geometry so simple that you can follow the whole argument in about 90 seconds, which is exactly what makes it lethal. Imagine you are standing in the middle of a very large space filled evenly with light bulbs of identical brightness. The ones near you look bright. The ones further away look fainter because brightness falls off with the square of the distance. Now ask how many bulbs you can see that are brighter than some threshold. To see fainter bulbs you have to look further out, and the volume you are surveying grows with the cube of the distance while the brightness falls with the square. Do the arithmetic and you get a fixed relationship. The number of sources brighter than a given level scales with that level to the power of -1.5. That is it. That number, -1.5, comes out of nothing but geometry. There is no cosmology in it at all. So here is the test. If the universe is in a steady state, if it genuinely looks the same at all times and therefore at all distances, then the population of radio sources you are counting has to obey that geometric slope. give or take the mild corrections that expansion introduces. But if the slope you actually measure is steeper than -1.5, that means there are more sources out there in the deep sky than the simple geometry allows. And because looking further away means looking further back, more sources at greater distance means more sources in the past than there are now. Which means the universe has changed, which is precisely the one thing the steady-state theory forbids, absolutely and by construction. Martin Ryle's group at Cambridge published the second Cambridge catalogue in 1955 and reported a slope of about -3. That is not a small excess. That is catastrophic, not just for the steady state, but for essentially every reasonable expanding model as well. And it was wrong. This part of the story deserves its own moment, because it is a very good example of how real science actually goes. 2 years later, Bernard Mills and Bruce Slee, working in Australia with a cross-shaped antenna near Sydney, showed that the great majority of the Cambridge sources were not sources at all. They were what astronomers call confusion. The Cambridge beam was broad. When 2 or 3 genuinely faint objects happened to fall inside it, the instrument reported them as one apparently brighter object, and the counts filled up with bumps that did not exist. Only about a quarter of those second catalogue sources survived into the next survey. The instrument had been designed on the assumption of roughly 1 source per beam area, and the modern rule of thumb is 1 source per 20 or 30 beam areas. Cambridge had been off by more than an order of magnitude in how carefully they needed to look. The fix was elegant. Peter Scheuer, working in Ryle's own group, realized that you do not have to resolve individual sources at all. You can extract the count statistically from the way the brightness of the map fluctuates from patch to patch, because a sky full of faint unresolved objects has a characteristic statistical signature even when you cannot pick out a single one of them. The technique is still used. It is how the Cambridge results and the Sydney results were eventually reconciled, and it is why the mature numbers can be trusted when the early ones could not. Those mature numbers came in the third Cambridge catalogue of 1959, 471 sources measured at 159 MHz, and its revised version in 1962, 470 sources at 178 MHz. The slope came out around -2, less spectacular than the 1955 claim. Still, and this is the only thing that matters, steeper than -1.5. The radio sky is not the same at all depths. There were more of these objects in the past than there are now. The universe has a history. Now we come to the room. In early February of 1961, the Mullard Electronics Company telephoned Fred Hoyle. Mullard had funded Ryle's new observatory at Cambridge, and they invited Hoyle and his wife Barbara to a press conference at their London headquarters, saying that Ryle would be presenting results that would be of great interest to him. That is what they told him. Results of great interest. Barbara was seated in the front row. Hoyle was put on the stage facing the assembled press. Ryle then stood up and gave, not a brief announcement, but a full technical lecture on the newest Cambridge survey. He went through the counts, he went through the slope, and he concluded that the numbers showed, unambiguously, a higher density of radio sources in the distant past than in the present day, and that the steady-state theory was therefore wrong. The theory that Hoyle had built, defended, and named the alternative to in front of the journalists with his wife in the front row. Then Hoyle was invited to comment. By the account drawn from his own memoirs, he was incredulous and humiliated. He managed a few sentences and left. He did not answer his telephone for a week. He did not attend the meeting of the Royal Astronomical Society on the 10th of February, where Ryle formally presented the result, and his student Jayant Narlikar gave the rebuttal in his place, having been coached beforehand with the very Hoyle-like instruction that he had 10 minutes for his talk and should make sure he said everything necessary in 8. Ryle telephoned Hoyle afterwards to apologise. He said he had had no idea how bad it would be. I do not tell you this to make Ryle the villain. He was one of the finest observational astronomers of the century. He invented the technique that made the counts trustworthy in the first place, and he received the Nobel Prize in 1974 for it, the first Nobel ever given for astronomical work. He was, by every account, not a cruel man. He simply walked into a situation that a public relations department had arranged, and did not understand what he was standing in the middle of until it was over. And notice what did not happen. Hoyle did not concede. He went on defending versions of a beginningless universe for another 40 years, well past the point where the microwave background had closed off the remaining escape routes, and he was still arguing at the end of his life. The man who named the Big Bang never accepted it. He gave it the name it still carries, as a way of dismissing it, and then watched it win, and never took the word back. And I want to be fair to him, because the caricature of Hoyle as a stubborn crank is both unkind and inaccurate. 4 years before that press conference, he had co-authored one of the most important papers ever written in astrophysics, working out how stars manufacture the heavy elements in their cores and scatter them when they die. He had predicted, in advance and against the expectations of the nuclear physicists, that carbon nuclei must have a particular energy state at 7.65 million electron volts, because otherwise stars could not make carbon, and therefore he could not be standing there thinking about it. They looked. It was there. That is one of the boldest successful predictions of the 20th century, and it is the reason there is carbon in your blood. When the Nobel Prize was eventually given for stellar nucleosynthesis in 1983, Hoyle was left off it, a decision widely regarded as one of the committee's clearest misjudgments. So this is not a story about a fool being corrected. It is a story about a first-rate mind that was right about where the atoms in your body came from, and wrong about where the universe came from, and that could not tell the difference from the inside. Nobody can. That is the entire reason we build instruments. So by 1965, when the leftover heat of the early universe was finally detected as a faint hiss at every point in the sky, the argument was effectively over. The universe had a hot, dense past. The theory that described it was in place. Which brings us to the part of this that nobody tells you. Because that theory, the one that won, the one we teach in schools and put in documentaries and describe as the story of how everything began, does not describe how anything began. It never did. It never even claimed to. Open any serious textbook on cosmology, turn to the chapter on the early universe, and look at where the first calculation starts. It does not start at zero. It starts at a temperature. Somebody has already lit the fire before the first equation appears on the page. That is not an oversight. That is the theory. The hot Big Bang model, the one that won the argument in 1961 and 1965, is a description of what happens to a universe that is already hot, already dense, already expanding, and already almost perfectly smooth. Given that starting condition, it derives an extraordinary amount. It tells you how the light elements form and in what proportions. It tells you that there must be a bath of leftover radiation filling all of space, cooled by expansion to a few degrees above absolute zero, and it gets the shape of that radiation spectrum right to a precision that has no real competition anywhere in science. It tells you how small variations in density grow under gravity into galaxies. It predicts the expansion history you actually see when you point a telescope at distant supernovae. Every one of those predictions has been tested, and every one of them has held. And on the question of where that hot, dense, expanding smooth state came from, it says nothing whatsoever. Not, we do not know yet. Nothing. The question is outside its scope by construction. The theory takes the initial conditions as given, as an input, as a set of numbers you write down at the top of the page before you start, and then it computes forward with tremendous accuracy. So when somebody says the Big Bang is our theory of how the universe began, they are describing a thing that does not exist. What exists is a theory of what the universe did next. But hold on, you might reasonably say. What about the singularity? What about the moment when everything was compressed to a single point of infinite density? That is in all the documentaries. That is the beginning. Here is where we have to be careful, because that idea is not a discovery. It is an extrapolation, and extrapolations are only as good as the theory you are extrapolating. Take general relativity, which is our theory of gravity and of the shape of space and time. Apply it to a universe filled with matter and radiation. Run the equations backwards. What you find is that the density climbs and the curvature climbs, and at a finite time in the past both of them go to infinity. That is the singularity. And in the popular telling, that infinity is treated as a physical fact, a real object, an actual point where the universe was actually squeezed to zero size. That is not what an infinity means in physics. When a physical theory hands you an infinity, it is not describing a location. It is telling you that you have driven it outside the range of conditions where it works, and that its answers past that point are not answers. It is the same kind of event as a bridge calculation returning a negative length. Nobody builds the negative bridge. Everybody checks the assumptions, and in this case the failing assumption is obvious and known. General relativity is a classical theory. It has no quantum mechanics in it at all. It treats space and time as smooth, continuous things, right down to any scale you like. But we have known for a century that at sufficiently small scales the world is not smooth and continuous, and the regime you're extrapolating into as the density approaches infinity is precisely the regime where the quantum nature of gravity cannot possibly be ignored. You're using a theory in exactly the conditions it was never built for, and then treating the nonsense it produces as a description of reality. Now, there is a beautiful and much misreported result attached to this. In the 1960s, Roger Penrose and Stephen Hawking proved a set of theorems showing that the singularity is not an artifact of assuming a perfectly symmetric universe. It does not go away if you make the model messier and more realistic. Under very general conditions, classical general relativity really does run into a place where the description cannot be continued. That is usually reported as proof that the universe began in a singularity. It is very nearly the opposite. What the theorems establish is that classical general relativity reliably, generically, predicts its own breakdown. It is a theory that tells you, in advance and with mathematical precision, where it stops being true. That is a remarkable property for a theory to have, and it is a much more interesting result than the version in the documentaries, because it means the singularity is not a feature of the universe, it is a feature of our description. So here is the honest state of affairs as of, say, 1978. We had a theory of the universe that worked forwards better than almost anything in science, and died backwards. It began in the middle of the story. It assumed a starting state it could not explain, and when you tried to push it back to the origin, it handed you a symbol that means the theory has stopped working. That is not a small gap to be filled in later. That is the entire question, still sitting there, untouched, underneath a mountain of confirmed predictions, and it is worth pausing on how strange the situation was, because I do not think most people appreciate it. We could tell you the ratio of hydrogen to helium in the universe to 2 decimal places and explain exactly why it has that value from nuclear physics measured in laboratories on Earth. We could tell you the temperature of space to 4 decimal places. We could tell you how old the whole thing was. And if you asked why there was a hot, dense, smooth, expanding universe there to have those properties in the first place, the correct professional answer was a shrug. Nor is that the only shrug. There is a second one, quieter, that gets even less attention. The hot Big Bang model also does not explain where the lumps came from. Its starting state is smooth, and a perfectly smooth universe under gravity stays perfectly smooth forever. Nothing collapses, because there is nothing for anything to collapse toward. To get galaxies, you need tiny variations in density, seeds, places where there is very slightly more stuff than average. And the model does not produce them. You have to put them in by hand alongside everything else, as another number written at the top of the page. There is a third one as well, and it is the one that will matter most later tonight, so I want to plant it now. Count the particles of matter in the universe and count the particles of light, and you find roughly 1 particle of matter for every 1.5 billion photons. Everything solid you have ever touched, the chair, the floor, your own hands, is made from that 1 in 1.5 billion residue. In the very early universe, matter and antimatter should have been produced in essentially equal amounts and should have annihilated each other completely, leaving nothing but radiation and an empty, sterile cosmos. Something tipped the balance by about 1 part in 1.5 billion, and that fractional excess is everything that exists. The hot Big Bang model does not explain that number either. It measures it and writes it down at the top of the page with all the others, so the model, in its classic form, requires you to assume a universe that is hot, dense, expanding, flat, smooth, and yet not quite smooth, in exactly the right way, at exactly the right amplitude, and containing exactly the right sliver of leftover matter. That is a great deal of assuming, and there is a wall in front of all of it that I should name plainly, because it is the honest edge of everything we are going to say tonight. It is called the Planck time, and it is about 5.410 millionths of a billionth of a billionth of a billionth of a billionth of a second. That is not a poetic number. It is the scale at which the quantum nature of space and time can no longer be treated as a small correction to a smooth background, because the correction is as large as the thing it is correcting. Every statement anyone makes about the universe earlier than that, including every statement in this video, is extrapolation without a theory to extrapolate with. We do not have a working quantum theory of gravity. Until we do, the Planck time is not a moment we know little about. It is a moment we currently have no vocabulary for, which raises the obvious question, and it is the question the whole rest of tonight turns on. If you have to assume all of that, how finely tuned does the assumption have to be? Could you get a universe like this one by accident, out of a reasonable range of starting conditions the way you get a snowflake or a river delta? The answer, when people finally sat down and worked it out, is no. Not remotely. Not by anything resembling accident. And the numbers involved are so absurd that for about 20 years the polite thing to do was not to bring them up. Pick a patch of sky directly above you, about the size of your thumbnail held at arm's length. Now pick another patch, on the far side of the sky, down near the opposite horizon. Point a sensitive enough instrument at each one and measure the temperature of the faint microwave glow coming from them. The first patch reads 2.7251 degrees above absolute zero. The second reads 2.7249. Those two patches have never met. Not in the sense of being far apart, in the strict physical sense. In the entire history of the universe up to the moment that light was released, no signal of any kind, travelling at any speed up to and including the speed of light, could have crossed from one of those patches to the other. They have no shared past. Nothing that happened in one could have influenced anything in the other. They are, in the language of relativity, causally disconnected, and they always have been, and they agree on their temperature to within 2/10,000ths of a degree. This is the horizon problem, and it is the first of three enormous and specific embarrassments sitting at the foundations of the model we have just spent an hour praising. Let me give you the scale of it properly. The light we're talking about was released about 380,000 years after the start, when the universe cooled enough for atoms to form and the fog cleared. At that moment, the largest distance any signal could have travelled since the beginning corresponds to an angle on the sky today of roughly 1 degree. Roughly twice the width of the full moon. Now divide the whole sky into patches 1 degree across. You get somewhere around 10,000 of them. 10,000 independent regions, each one sealed off from all the others, each one with no possible way of learning what temperature the rest had settled on. And all 10,000 of them arrived at the same answer, to 1 part in 100,000. Alan Guth, who is going to become the central figure of this story in a few minutes, has an image for how absurd this is that I have always loved. Imagine, he says, that the universe is populated by little purple creatures, each one equipped with a furnace and a refrigerator, whose job is to go around making sure the temperature comes out the same everywhere. Those creatures would have to communicate with each other at roughly 100 times the speed of light to have finished the job in the time available. Something made the sky uniform. Nothing in the theory can have. Notice the shape of that failure, because the next two have the same shape. It is not that the model contradicts an observation. Nothing here is inconsistent. It is that the model requires a starting condition of extraordinary and unexplained specificity, and then shrugs when you ask where that specificity came from. The second problem is about the shape of space, and it is worse. The geometry of the universe depends on how much stuff is in it. Put in more than a certain critical amount and space curves in on itself like the surface of a sphere. Put in less and it flares outward like a saddle. Put in exactly the critical amount and it is flat, in the sense that parallel lines stay parallel and the angles of a triangle add to 180 degrees no matter how large you draw it. We measure our universe to be flat, or so close to flat that we cannot detect the difference. That sounds like a pleasant, tidy result. It is a catastrophe, because flatness is unstable. Think of a pencil balanced upright on its point. There is exactly one position where it stays. Any deviation, however tiny, grows, and grows faster the larger it gets, until the pencil is lying on the table. The density of the universe behaves the same way. Exactly critical is a balance point, and any departure from it amplifies with time, which means that if the universe is still near flat after nearly 14 billion years, it must have started staggeringly close to exactly flat. Guth worked out how close. 1 second after the beginning, he found, the density had to equal the critical density to 15 decimal places. Not 15%, 15 decimal places, somewhere between 0.9999999999999 and 1.0000000000000000001 times the critical value, or you do not get a universe that looks anything like this one. Push the calculation all the way back to the Planck time, and the required precision is something like 1 part in 10 to the 60th power, though the exact exponent people quote wanders between 60 and 62 depending on assumptions. 10 to the 60th. To give that a shape you can hold, there are somewhere around 10 to the 80th atoms in the observable universe. So the fine-tuning required is roughly the same as picking out a specific group of 100 billion atoms from the entire cosmos, blindfolded, on the first try. And the model has no mechanism to produce that. You write it down, you hope nobody asks. Now, there is a serious objection to calling this a problem at all, and I want to give it a fair hearing rather than skip past it, because a good fraction of thoughtful people land on it independently. The objection runs like this. Any value the density could have taken would have been some specific number, and every specific number is equally improbable in advance, so singling out this one as suspicious is a mistaken reasoning. You're being amazed that the lottery had a winner. The answer is the pencil. It is not the specificity that is the problem, it is the instability. If the density had started well away from critical, the universe would have either recollapsed within moments, or thinned out so fast that gravity never assembled anything, and in both cases there would be no stars, no planets, and nobody available to notice. Every history except the balanced one is short and empty. The universe did not merely land on an improbable number, it landed on the one number that runs away from itself, and then stayed near it for nearly 14 billion years. That is not a lottery winner. That is a pencil that has been standing on its point since the Bronze Age and shows no sign of falling, and it is worth saying what a monopole would actually be, because the word sounds abstract and the object is not. Every magnet you have ever handled has two poles. Break it in half, and you do not get a north and a south. You get two smaller magnets, each with both. That is not a limitation of the manufacturing. As far as anyone has ever observed, isolated magnetic poles simply do not exist in nature, and one of the unresolved oddities of physics is that nothing in the fundamental equations forbids them. Grand unified theories not only permit them, they insist on them, and they insist on them being heavy. A single one would weigh something like 10,000 trillion times the mass of a proton, compressed into a knot far smaller than a proton is wide. One of them would be an object you could, in principle, hold, and it would weigh about as much as a bacterium, and it would be a stable topological accident left over from the moment the forces of nature separated from each other. This is not, incidentally, a lonely prediction. The same mechanism, worked out by Tom Kibble in 1976, produces a whole family of these leftover snags depending on how the symmetry breaks. Points, which are monopoles, lines, which are cosmic strings, and sheets, which are domain walls. The monopole problem is one member of a household, and the household is one of the more haunting ideas in physics, because every one of them would be a permanent scar in the structure of space marking where the early universe made a choice. The third problem came from a completely different direction, and it is the one that actually matters for the plot, because it is the problem somebody was working on when they accidentally solved the other two. In the 1970s, particle physicists were building grand unified theories, attempts to show that the strong nuclear force, the weak nuclear force, and electromagnetism are three faces of a single force that only look different because the universe cooled down and the symmetry between them broke. These theories are elegant, and they make a prediction that nobody wanted. When that symmetry breaks, the breaking does not happen the same way everywhere at once. Different regions choose different orientations, and where mismatched regions meet, the geometry gets snagged. The snags are stable, they cannot unwind, and they behave as particles. Specifically, they behave as magnetic monopoles, isolated north poles with no south, each one absurdly heavy, and each one permanently stable. The trouble is how many of them you get. As a rule of thumb, you produce about one per causally connected region at the moment of the transition, and at that early stage the causally connected regions are tiny, so you produce a colossal number of them. Yakov Zeldovich and Maxim Klopov raised the alarm in 1978. In 1979, John Preskill at Harvard put the numbers down properly in a paper received on the 21st of June and published on the 5th of November, and the abstract contains one of the great understatements in the literature. The density of such monopoles in the early universe, he wrote, is estimated to be unacceptably large. Unacceptably large means the monopoles would outweigh everything else so heavily that the universe would have recollapsed long before any of this. The predicted abundance overshoots the observational limits by many orders of magnitude. The actual number of magnetic monopoles anybody has ever detected, incidentally, is 0. So there are your 3. The sky is uniform across regions that never touched. Space is flat to a precision no mechanism produces, and the best particle theories of the era predict a universe choked with heavy objects that are not there. 3 separate diseases in 3 separate areas of physics, all with the same symptom, a starting condition so specific that calling it a coincidence stops being intellectually respectable. And now the detail that makes the next part of this story land properly. Look at the acknowledgements section of Preskill's monopole paper, the one that says unacceptably large. Among the people thanked for useful discussions is A. Guth. Because Alan Guth was not trying to explain the origin of the universe. Nobody hires you to do that. He was a 32-year-old postdoc working on a technical particle physics problem, trying to find a way to suppress the production of magnetic monopoles so that the grand unified theories would stop predicting a universe that could not exist. He was trying to get rid of the monopoles, and on a December night in 1979, following that one narrow problem, he walked into something considerably larger. There is a notebook in a museum in Chicago, in the collection of the Adler Planetarium, and on one of its pages a man has written 2 words in capital letters and drawn a box around them. The words are spectacular realization. The date is the 7th of December, 1979. The man is Alan Guth, 32 years old, a postdoctoral researcher at the Stanford Linear Accelerator Center, which is not a permanent job and was not at that point leading anywhere in particular. He had come to the calculation the previous night, the 6th, at the rented house in Menlo Park where he was living with his wife and their small son. He had been working, as we said, on magnetic monopoles, on the narrow technical question of how to stop the grand unified theories from filling the universe with them. And somewhere in the middle of that, following the equation sideways, he found that the answer to the monopole problem also erased the horizon problem, and also erased the flatness problem, and did all 3 at once with a single mechanism. The next morning he got on his bicycle and rode to his office at the Accelerator Center. He later recorded the time, 9 minutes and 32 seconds, which he noted was a record. Leonard Susskind, one of the first people he told, said the most amazing thing is that they pay us for this. Let me show you what he had found, because it is genuinely simple once you see it, and I think the simplicity is why it took until 1979 for anyone to notice. Start with an ordinary substance, air, water, a gas of particles, radiation. Put it in a box and let the box expand. What happens to the density? It falls. There is the same amount of stuff spread through more volume, so there is less of it per unit of space. That is so obvious it barely feels like physics. Now consider something different. Consider a field filling all of space, sitting not at the lowest point of its energy but in a temporary dip further up the slope. It is stuck there, at least for a while, the way water can sit in a shallow depression on a hillside rather than running to the bottom. That configuration has energy, and here is the crucial property, that energy belongs to the vacuum itself, to the state of space, not to any material sitting inside space. So what happens when the box expands? Nothing. The energy density stays exactly the same because there is simply more space, and every cubic meter of space carries the same energy as before. You have doubled the volume and doubled the total energy, and the density has not moved. That is a substance that does not thin out. And in general relativity, a substance that behaves that way has a very strange property. It has negative pressure, and negative pressure, in Einstein's equations, gravitates the wrong way. It pushes. The result is not an explosion. This is the point I want you to hold on to, because it is the thing the 1949 name makes impossible to see. Nothing is flying through anything. Space itself doubles in size, and then doubles again, and then again, at a fixed and constant rate, for as long as the field stays stuck in that dip. Each doubling is what cosmologists call an E-fold. The process is called inflation. And how many doublings do you need to fix everything? To solve the horizon problem you need somewhere between about 40 and 60, with the exact figure depending on details we will come to. 60 doublings does not sound like a lot. 60 doublings is a factor of roughly 10 to the 25th in linear size, which is Guth's own figure, with no upper limit on how much more you might get. In volume, that is at least 10 to the 75th. The patch of space that has now become everything you can see through every telescope may have begun as something around 10 to the minus 24 centimeters across, 100 billion times smaller than a single proton. Now watch the 3 diseases cure themselves. The horizon problem asked how 10,000 disconnected patches of sky could agree on a temperature. The answer is that they were never disconnected. Before inflation, the whole region was small enough to be an easy contact, everything thoroughly mixed and equalized, and then inflation took that one tiny thermalized patch and stretched it until it was larger than everything we will ever see. The sky's uniform because it used to be one thing. The flatness problem asked why space is so precisely flat. The answer is that any curvature gets stretched away. Take a small ball, a marble, and inflate it to the size of the Earth. Stand on it. It looks flat, not because it was made flat, but because you are now looking at a very small piece of something enormous. Guth uses exactly that image. Inflation does not fine-tune the density. It drives the density toward critical, automatically, from almost any starting value, because the stretching flattens whatever is given, and the monopoles, the problem he actually set out to solve, are simply diluted away. They were made before or during the stretching, and the stretching increases the volume by a factor of 10 to the 75th, so their density drops by the same factor, and the expected number in the entire observable universe falls to something on the order of 1, which is why nobody has ever found one. 3 problems, 1 mechanism, 1 night. The paper is called Inflationary Universe, a possible solution to the horizon and flatness problems, and it appeared in Physical Review D, Volume 23, pages 347 to 356. It was received on the 11th of August 1980 and published on the 15th of January 1981. It has since been cited by something approaching 8,000 papers. And now I have to tell you the part that makes me admire the man, because the most remarkable thing in that paper is not the mechanism. It is the last section, in which Guth carefully demonstrates that his own model does not work. The problem is how inflation stops. In Guth's original version, the field escapes its dip by quantum tunneling, which happens locally, in bubbles. A bubble of the true lower energy state forms somewhere, and grows, and inside it inflation has ended, and the energy has been released. Fine. Except that the space between the bubbles is still inflating, and inflating fast, so the bubbles are being carried away from each other faster than they can grow into one another. They never merge into a smooth whole. They form isolated clusters dominated by single large bubbles, and the uniform, thermalized universe the whole scenario was supposed to produce never appears. Guth and Eric Weinberg worked this out in detail in a 1983 paper, and the conclusion was unambiguous. So Guth published the idea with the failure attached. His own closing line in the 1981 paper is that the scenario seems to lead to some unacceptable consequences, so modifications must be sought. Michael Turner's description of how that landed is the best summary I know of what makes a scientist worth listening to. One of the striking things about the paper, Turner said, was that he told everyone, "Look, guys, the model I am putting forward does not work. I can prove it doesn't work, but I think the basic idea is really important." He was right on both counts. David Kaiser, the historian and physicist at the Massachusetts Institute of Technology, puts the same point more directly. In his own first article, the one that introduced much of the world to cosmic inflation, Kaiser says, Guth pointed out the fatal flaw for his own idea. Kaiser takes that as a sign not just of carefulness, but of relentless scientific honesty. And it is worth dwelling on for a second, because the incentives in any competitive field run hard the other way. The easy move, the human move, is to leave the last section out, publish the beautiful mechanism, and let somebody else find the hole in a year or 2. He did not do that. He handed over the mechanism and the hole together in the same paper and asked for help. The modifications arrived fast. Andrei Lindy in Moscow found the fix about a year later. He has described the moment, the middle of the night, waking his wife, telling her he thought he knew how the universe was created. His solution, published in Physics Letters B in 1982, is called New Inflation, and it removes the bubbles entirely. Instead of being trapped in a dip and tunneling out, the field sits on a very gently sloping plateau and rolls down it slowly. Inflation happens while it rolls, and it ends smoothly when the slope steepens near the bottom. One region inflates into everything we see, so there is nothing to merge and no percolation problem to solve. Andreas Albrecht and Paul Steinhardt published the same idea independently in Physical Review Letters on the 26th of April 1982. Remember Steinhardt's name. He's going to come back later tonight from an unexpected direction. Linda followed up in 1983 with chaotic inflation, which abandoned the phase transition framing altogether and showed that you did not need any of the grand unified apparatus. You just need a field and a suitable slope, and the initial conditions can be almost anything. And underneath all of it there is a prior claim, which the field is generally scrupulous about acknowledging. Alexei Starobinsky, also in Moscow, had constructed a model in 1979, published in 1980, in which quantum corrections to Einstein's equations produce exactly this kind of exponentially expanding phase. He got there first, but he was solving a different problem, trying to avoid the singularity rather than to explain the smoothness and flatness of the sky, and as Linda later put it, with what I choose to hear as affection rather than condescension, Starobinsky didn't know why this would be interesting. So by 1983 the mechanism was in place, in 3 or 4 versions, and it worked. It explained why your sky is smooth. It explained why space is flat. It explained where the monopoles went, and it left behind a consequence that almost nobody outside the field has ever been told, which is the reason this video has the title it has. Because if inflation happened, then the hot dense fireball everybody calls the beginning of the universe is not the beginning of the universe at all. It is what happened when inflation stopped. Picture the universe at the instant inflation finishes, and then throw away everything you are picturing, because it is wrong in the most interesting possible way. You're expecting a fireball, heat, light, density, violence. That is what the phrase the early universe means to everyone, and it is what every illustration has shown you since you were a child. A blazing point, a white-hot expanding cloud. The actual state is the exact opposite of that. At the end of inflation, the universe is the coldest, emptiest, darkest, most featureless condition physics is able to describe. Here is why, and it follows directly from what inflation is. Exponential expansion is exponential dilution. Anything that was in that patch of space before inflation started, any particles, any radiation, any structure, any lumps, any monopoles, any record of any prior state whatsoever, gets its density divided by the volume increase. And the volume increase is that factor of 10 to the 75th or more. Run the arithmetic for 60 doublings, and the number densities fall by something like 10 to the 78th. That is not thinning. That is annihilation by geometry. Take a room containing every particle in the observable universe, expand it by that factor, and you are left with, on average, considerably less than 1 particle. Whatever was there before is not merely rare afterwards, it is absent, and the temperature falls with it, because temperature is just the energy of the things that are moving around, and there is nothing left to move. Linda has said this plainly. The stretching erases all memory of the boundary conditions. Whatever gradients existed, whatever particles existed, become exponentially small. Inflation does not merely explain the universe's initial conditions. It destroys the evidence of what preceded them, thoroughly and irreversibly as an unavoidable consequence of the mechanism. So picture it properly now. You're standing in a universe that has just finished inflating. There is no light here, because there are no photons, and even if there were, you would have nothing to see. There is no sound, because there is no medium, and there never was. The temperature is as close to absolute zero as anything in the history of the cosmos has ever been or will ever be. Every direction you turn is identical to every other, not approximately, but to a level of sameness that has no parallel in ordinary experience. Space has been pulled so flat that the concept of curvature has stopped meaning anything on any scale you could measure. There are no particles, there are no lumps, there is no structure, there is nothing anywhere to distinguish here from there, and it is not empty. That is the part that will not sit still in your head. Filling every cubic millimetre of that dark, freezing, featureless space is a single field, perfectly uniform, holding still. Not a substance, not a gas, a condition of space itself, with a value, and that value carries energy. And the amount of energy it is holding is every joule that will ever become a hydrogen atom, a star, a planet, an ocean, a redwood, a hand, all of it, not scattered, not distributed. Concentrated in the configuration of one motionless thing, everywhere at once. Nothing is happening. Nothing has ever happened here. Then the field begins to slide. When inflation ends, the slope the field has been rolling down steepens near the bottom, and the field stops rolling slowly and starts to fall. It overshoots the minimum, swings back, overshoots again. It oscillates. and a rapidly oscillating field coupled to other fields does what a rapidly oscillating anything does when it is coupled to something else. It transfers its energy. That transfer has a name. It is called reheating, and reheating is the hot Big Bang. That is the whole claim of this video in 6 words, so let me lay out what it means before we test it. The fireball is not the origin. The fireball is what inflation left behind when it dumped everything it was carrying. The dense hot particle soup that the classic theory takes as its unexplained starting condition, the state everybody calls the beginning of the universe, is on this account the exhaust of a process that had already been running. It is the ash, not the fire. This is not a fringe reading. Daniel Bauman's standard graduate lectures on primordial cosmology put it in almost these words. The space-like singularity of the standard Big Bang is replaced by the reheating surface, and rather than marking the beginning of time, it simply corresponds to the transition from the end of inflation to the standard evolution. Guth's own popular essay on the subject, written in 1997, is actually titled, "Was Cosmic Inflation the Bang of the Big Bang?" His answer in that essay, eventually the false vacuum decays, and the energy that had been locked in it is released, producing a hot uniform soup of particles, which is exactly the assumed starting point of the traditional theory. David Kaiser is blunter. The reheating period, he says, sets up the conditions for the Big Bang, and in some sense puts the bang in the Big Bang. It is the bridge period where all hell breaks loose and matter behaves in anything but a simple way. Reheating, in his phrase, was an insane time when everything went haywire. And notice what quietly resolves itself if that is true. Remember the 2 words we took apart at the very start of the night. It isn't a bang because there was no medium and no sound. And now it turns out that it isn't a bang for a much better reason than that. There was no explosion because nothing exploded. A field that was the same everywhere fell everywhere, simultaneously, and the entire volume ignited at once, not from a point, not spreading outward from a centre into surrounding emptiness, everywhere, all at the same instant because the thing that fell was uniform and had no centre to fall from. Hoyle's insult was more accurate than his cosmology. Now, for about a decade after inflation was invented, physicists assumed reheating was a slow and rather boring business. The picture was perturbative. The field is essentially a population of particles, and they decay one at a time into other particles at a rate set by how strongly they are coupled, the way a radioactive sample decays. Steady, gradual, not very interesting. In 1994, that picture was overturned by Lev Kaufman, Andrei Linde, and Alexei Starobinsky in a paper called Reheating After Inflation, received on the 2nd of June and published on the 12th of December in Physical Review Letters. They expanded it into a much longer treatment in Physical Review D in September of 1997, and what they found is that the first stage is not gradual at all. The mechanism is something you have used yourself on a playground. When a child pumps a swing, they are not pushing against anything. They are changing the effective length of the pendulum in time with its own motion, twice per cycle, and the amplitude grows exponentially. That is parametric resonance. It is the difference between pushing a swing and driving it, and it is enormously more efficient. The oscillating field does the same thing to every field coupled to it. Its oscillation modulates the effective mass of those fields in time with itself, and particle production runs away, not particle by particle, exponentially, non-perturbatively, in a burst. Kaufman, Linde and Starobinsky called this first stage preheating. Their description of the regime is unusually vivid for a technical paper and worth hearing nearly as they wrote it. The resonance in this model, they say, is very broad, and it occurs in a very unusual stochastic manner. Quantum fields interacting with the oscillating field experience a series of kicks which occur with phases uncorrelated to each other. They name that stochastic resonance. The process runs in stages. First, the particles being created are too few to matter. Then their back reaction actually increases the frequency of the field's oscillations, making the process even more efficient than before. And finally, the particles start scattering off each other hard enough to shut the resonance down. And under some conditions, it produces particles far heavier than the field that is producing them, which is to say heavier than anything that could ever have been made in thermal equilibrium at that temperature. How fast? The honest answer is that there is no single number, because it depends on the model. The literature says the resonant creation lasts a few periods of the oscillation, and for the simplest potentials, preheating is essentially complete within a handful of swings. lattice simulations run at the Massachusetts Institute of Technology in 2019 found the whole transition completing over 2 to 3 doublings of the universe against inflation's own 60, 2 or 3 doublings. From the coldest, emptiest condition in the history of everything to a thermalized fireball dense enough to run nuclear reactions. Now think about what else has to happen in that window, because this is where the thread I planted earlier comes back. Remember the one particle of matter for every 1.5 billion photons, the sliver of leftover matter that everything solid is made of. Whatever tipped that balance had to operate in a universe that already contained particles, which means it could not have happened during inflation, because during inflation there were no particles to be unbalanced. It has to happen at or after reheating. So if this account is right, the moment we call the beginning of the universe is also the moment matter chose a side. The fire that lit everything is the same event in which the universe decided, by some mechanism still argued about, that there would be something rather than an equal quantity of nothing cancelling itself out. The two most fundamental questions you could ask about existence, why there is anything and why it is hot, get answered in the same handful of oscillations of a falling field. And I should be honest that this is also the part of the story where the physics is thinnest. Richard Easter, at the University of Auckland, put it with admirable directness. There are hundreds of proposals for producing the inflationary phase, but the transition between the inflationary phase and the so-called hot Big Bang is the least understood part of the story. We have a mechanism. We do not have a settled model. If the field is coupled weakly enough, some of it survives the whole process and is still with us, which is one of the live candidates for dark matter, meaning the stuff that drove inflation might also be the invisible material holding the galaxies together. If preheating is as violent as the simulation suggests, it would have produced a hiss of gravitational waves at frequencies far above anything any instrument on Earth can currently hear, and building the instrument that could hear it is not a funding problem, it is a physics problem nobody has solved. And here is the thing I find genuinely humbling about all of this. We do not know how hot it got. The lower bound is firm because the fire has to be hot enough, early enough, to run the light element reactions and thermalize the neutrinos, and that puts a floor on it. Steen Hannestad's 2004 paper, which is helpfully titled What is the Lowest Possible Reheating Temperature, gives about 4 million electron volts, and a 2015 analysis using data from the Planck satellite tightened it to 4.7. The upper bound comes from the fact that we have never detected the gravitational waves inflation should produce, which caps the energy scale, and under the most efficient assumptions gives a ceiling somewhere around a few times 10 to the 15th billion electron volts. In supersymmetric models it is far lower, closer to 10 to the 9th, because otherwise you overproduce particles that would wreck the light elements. Set the floor beside the ceiling, and the window is about 18 orders of magnitude wide. We can date the first 3 minutes of the universe to the second. We can tell you the temperature of space today to 4 decimal places, and we cannot say, within a factor of a quintillion, how hot the fire was that started it. Which is a good moment to stop and gather up what we actually have, because we have covered a great deal of ground, and I want to make sure it is all sitting in the right order before we go looking for the evidence. Let the fireball fade for a minute. Put the falling field down. We are going to stand still and count what is in our hands, slowly, because the second half of tonight goes somewhere the first half could not have gone without this. There are 3 things. The first is about a word. On a March evening in 1949, a man who did not believe the theory gave it a name designed to make it sound absurd, and the name won so completely that it now supplies the mental picture for almost everyone on Earth. That picture contains a sound that could not have existed, a location that does not exist, and a first moment that may not be a coherent idea. We have been carrying somebody else's dismissal around as though it were a description. The second is about a theory. The model that actually won, the one supported by the light elements and the microwave glow and the radio source counts, is not a theory of the beginning. It is a theory of the aftermath. It starts with a universe that is already hot, already dense, already expanding, already flat, already smooth, already carrying a precise sliver of leftover matter, and already faintly lumpy in exactly the right way, and from that it derives nearly everything with astonishing accuracy. Where that starting condition came from is not a question it answers, it is a question it declines to ask. And the third is about a mechanism. If, before the hot dense phase, the universe went through a brief interval of exponential stretching, then every one of those unexplained starting conditions stops being a coincidence and becomes a consequence. The sky is uniform because it was one small connected patch before it was stretched. Space is flat because everything looks flat when you enlarge it enough. The monopoles are missing because they were diluted into nothing, and the hot, dense phase itself, the fireball, the thing we call the Big Bang, is what happened when that stretching stopped and the field that had been driving it fell over and released everything it was holding. The beginning is an ending. I want to say that once more, quietly, because it is the sentence the whole night has been walking toward, and it is easy to let it slide past. The event you have always been told was the origin of the universe is, in the leading account, the closing moment of something else. The fire had already burned. What we can see is the ash. Now sit with the size of that for a moment, because there is something in it that is more unsettling than any explosion. Everyone assumes the beginning of the universe was loud and violent and blindingly bright. It was not. Immediately before it, on this account, the universe was the emptiest and coldest and quietest it has ever been. There was nothing to see and nothing to hear and nothing to touch and nothing happening at all, and every ingredient of every star and every living thing was folded into the value of a single, motionless field, filling everything, doing nothing. The silence is worse than the fire. I find I can picture the fire. I have never quite managed to picture the silence. Part of the reason, I think, is that we have no experience of anything genuinely uniform. Even the calmest thing you have ever seen has texture in it somewhere. A still lake has a shoreline, a dark room has a door, a silent night has your own pulse in it. There has never been a moment in your life when you were surrounded by something with no features anywhere, in any direction, at any scale. And that condition, which the human nervous system has no template for at all, is where everything came from. And now we arrive at the problem that the second half of the night has to solve, because if you have been listening carefully you will already have found it, and it is a serious one. Inflation erases its own tracks. That is not an incidental feature. It is the mechanism working as designed. Anything that existed before gets diluted by a factor with 78 zeros in it. Any record, any structure, any leftover, any evidence of any kind, gone. So inflation is a story about something that happened before the earliest thing we can see, and which took care to remove every trace of itself, and which ended by producing exactly the state that the old theory simply assumed. Which raises the obvious objection, and you should feel entitled to raise it. How could anybody possibly know? If the process wiped the slate, what is the difference between saying inflation happened and saying a very convenient thing happened for which no evidence can exist? That is not a hostile question. It is the correct question, and versions of it have been put to the field by extremely serious physicists, including, as we'll see, one of the people who invented the thing. So here is the answer, and it is the reason this is science and not a story. Inflation did leave something behind. Not a fossil, not a relic, not an object anyone could go and dig up. It left a number, and that number has now been measured to 4 decimal places. There is a line in a scientific paper published in 2020 that reads, in effect 0.9649 plus or minus 0.0042, 9 digits, a decimal point, 2 error bars. It is the most ordinary-looking thing you will hear tonight, and I am going to spend the next 20 minutes explaining why it is not. Start with the problem inflation appears to create for itself. If exponential stretching smooths everything out, and I mean everything, then the universe at the end of it should be perfectly featureless. Perfectly featureless is disaster, because a perfectly smooth universe under gravity stays perfectly smooth forever. There is nowhere for matter to fall toward. No stars form, no galaxies form, nothing forms. You need lumps. So inflation seems to solve the smoothness problem by making the universe too smooth, and the resolution of that is the single most beautiful piece of reasoning in modern cosmology. The field driving inflation cannot hold perfectly still. Nothing can. The uncertainty principle forbids any field from having both a definite value and a definite rate of change, which means that at every point in space the field is faintly, unavoidably jittering. These are quantum fluctuations, and they are as small as you would expect quantum things to be. Microscopic, fleeting, and ordinarily of no consequence whatsoever at any scale a human being would care about. But the space they are sitting in is doubling, and doubling, and doubling. So a jitter that appears on a scale far smaller than a proton gets stretched. Its wavelength grows with the expansion, and it grows fast, and very quickly it becomes larger than the distance light can cross in the time available. At that point something strange and important happens. The fluctuation stops behaving like a quantum wave. It cannot oscillate anymore, because the two sides of it can no longer talk to each other. It freezes. It becomes a fixed, classical variation in the energy of that region of space, and it just sits there while inflation continues to inflate around it. Then inflation ends. The horizon starts growing again faster than space does. And one by one, in order of size, all those frozen variations come back inside the observable region. The little ones first, then the bigger ones, over hundreds of millions of years, and each one arrives as a region where the density is very slightly above or below average. Gravity does the rest. Every structure in the universe on this account is a magnified quantum fluctuation. Not metaphorically, mechanically. The reason there is a galaxy here rather than nowhere is that a field twitched, once, before there was any matter to twitch about, and the twitch got stretched until it was the size of the sky. Now, the history of this idea needs some care, because the popular telling gets the priority wrong and the actual story is more interesting. The first calculation of it belongs to Vyacheslav Mukhanov and Gennady Chibisov in a paper published in JETP Letters in 1981. They showed that quantum fluctuations in an exponentially expanding phase produce a spectrum of density variations capable of forming galaxies and clusters, and that the spectrum comes out approximately the same at all length scales. That is remarkable work. But you will sometimes hear that it predates Guth, and it does not. Guth's paper was received in August of 1980. What it does predate is the inflationary perturbation calculations that became canonical, and it was done in the context of Starobinsky's model, which genuinely does predate Guth. There is an ongoing and rather bruising priority dispute about all of this, which I am going to name and then decline to adjudicate, because I do not think anybody outside it can. The calculations that the field actually built on came out of 3 weeks in Cambridge in the summer of 1982. The Nuffield workshop on the very early universe ran from the 21st of June to the 9th of July, and 4 separate groups spent it working the same problem in parallel. Stephen Hawking, Starobinsky, Guth working with So-Young Pi, and James Bardeen working with Paul Steinhardt and Michael Turner. They started with different methods and different answers. By the end they had converged. That convergence is the moment inflation turned from an appealing story into a theory that predicts a number. Here is the number, and here is why it is not one. If the amplitude of those primordial variations were exactly identical at every length scale, the spectrum would be what is called scale invariant. Edward Harrison in 1970 and Yakov Zeldovich in 1972 both proposed exactly that, on general grounds, essentially because there is no obvious reason for the universe to prefer any particular size. In the technical language, scale invariance corresponds to a quantity called the scalar spectral index having the value 1 precisely. Inflation says it cannot be 1. It says the index must be slightly less. The reason is physical and simple. During inflation, the field is not sitting still, it is rolling. Slowly, but rolling. Which means the energy driving the expansion is very gradually decreasing, which means the expansion rate is very gradually decreasing, and fluctuations do not all freeze out at the same moment. The largest ones, the ones that will end up spanning the sky, leave the horizon early, when the field is higher up the slope and the expansion is faster. The smaller ones leave later, when things have slackened slightly. So the big ones freeze out at a marginally higher energy than the small ones. The spectrum acquires a slight lean, slightly more power on small scales than on large. Cosmologists call it a red tilt, and crucially the size of the tilt is not arbitrary. It is fixed by how fast the field rolls, which is fixed by the shape of the slope it is rolling down, which is fixed by whatever physics was actually driving the inflation. The tilt is a measurement of the terrain. Michael Turner has been making this point for decades, and I think his phrasing is the cleanest available. One of the things he has tried to emphasize for 20-some years, he says, is that inflation does not predict scale invariance. It predicts almost scale invariance. Almost. That word is the whole scientific content, because if you go and measure the microwave background carefully enough and map how much variation there is at every angular scale across the whole sky, you can extract that index. The Planck satellite did it. Combining temperature, polarization and gravitational lensing, the 2018 results give a scalar spectral index of 0.9649, plus or minus 0.0042. It is not 1. And it is not 1 by a margin that is not remotely arguable. Depending on which combination of the data you use, Exact scale invariance is excluded at between 6.5 and 8.5 standard deviations, and if you fold in the measurements of the baryon acoustic scale from galaxy surveys, it goes to nearly 9. To put 9 standard deviations in perspective, particle physicists call 5 sigma a discovery. Guth's own reaction to living long enough to see this is one of my favourite things any physicist has said about their own work. He really never thought, he says, that anybody would ever actually measure these things. He thought they were just calculating for the fun of it, and now they are measuring them with such high precision that it really is just fantastic. Now let me tell you what you are actually holding when you hold that number, because I do not want it to slide past as a statistic. 0.9649 is not a measurement of the early universe. We have plenty of those. It is a measurement of the rate at which a field rolled down a slope, in an interval that finished before there was any heat, any light, any matter, any particle, or any event of the kind that we ordinarily mean when we use the word event. It is a measured quantity, with error bars, describing something that happened before what everybody calls the beginning. And the same variations it describes are the reason there is a Milky Way rather than a uniform grey fog, and therefore a sun, and therefore a planet, and therefore a species, and therefore you, lying there in the dark. The gap between 0.9649 and 1.0000 is not a rounding error. It is the width of the door everything came through. That is what I find hard to get used to. Not that it is ancient or violent or enormous, that it is a decimal, that the antecedent of everything turns out to be 4 digits on a page, and that we know them. And while we are here, notice how small the variations themselves are. The amplitude is about 1 part in 100,000, which is the same figure as the temperature uniformity we talked about earlier, because they are the same measurement seen from 2 directions. The universe arrived from inflation almost perfectly smooth, with departures of 1,000th of a percent, and that 1,000th of a percent was enough. Gravity is patient. Given 14 billion years, it took differences too small to detect with any ordinary instrument, and built every galaxy out of them. 2 other things fell out of the same maps, and both of them are quietly enormous. The pattern of hot and cold spots has a characteristic angular size, a standard ruler, and measuring how large it appears tells you the geometry of the space the light crossed to get here. It comes out flat to well under 1%. That is inflation's other headline prediction, sitting there confirmed. And the tilt itself does not appear to change with scale, which is exactly what a field rolling slowly down a gentle slope should produce, and not what most alternatives would. Now, a single number, however precise, is not proof of anything by itself, and you would be right to be suspicious of a theory that gets to be confirmed by one measurement. So here are the other 3 briefly, because they matter, and they are less famous than they should be. The first is that the variation should be adiabatic. Inflation converts the fluctuations of one field into density variations, which means every kind of matter should vary together, in step, in the same proportions. Photons, ordinary matter, dark matter and neutrinos should all be slightly denser in the same places. The alternative is what is called an isocurvature perturbation, where the components trade against each other, more of one and less of another. Those would show up as a distinctive signature in the sky, and Planck constrains any such contribution to the observed temperature variance to about 1 1/3% for dark matter and about 1 7/10% for the neutrino modes. The universe's lumps move together. The second is that the variation should be Gaussian. Fluctuations from a nearly free quantum field should have no preferred sign and no exotic higher-order structure. Planck's 2018 analysis measures the relevant parameter as -0.9 plus or -5.1, which is a slightly comic way of saying 0 and which rules out entire families of alternative mechanisms that would have produced obvious lopsidedness. And the third is the one that I think should be far more famous than it is, because it is as close to a direct observation of the pre-hot universe as anything we have. The microwave background is not only hotter and colder in different directions, it is also polarized, and the pattern of that polarization is correlated with the pattern of the temperature. Now, the temperature tells you about the density of the primordial plasma. The polarization tells you about its velocity, and on large angular scales that correlation goes negative. Density and velocity are anti-correlated, in a broad band across the sky, phase-locked, exactly out of step. Here is why that matters. Those angular scales are larger than the distance any signal could have crossed by the time the light was released. The density in one place and the motion in another have arranged themselves into a matched pattern across a gap that nothing could have travelled. No process operating inside the horizon can do that, because the two regions could not have coordinated. Something had to set the pattern up before the regions were separated. The team that first measured it clearly, led by Hiranya Peiris using the first year of data from the microwave anisotropy probe in 2003, said it flatly in their abstract. The detection of a large-angle anti-correlation in the temperature polarization cross-power spectrum is the signature of adiabatic super-horizon fluctuations at the time of decoupling. Read past the vocabulary and it says, "We have observed a pattern that was already in place before the universe was old enough for it to have been arranged." So that is the case. A tilt that inflation predicted in advance, and nothing else did. Lumps that move together, fluctuations that are Gaussian, and correlations stretching across distances that light could not have crossed. It is a good case. It is not a complete one, and the field knows exactly what is missing, because there is a fifth prediction, and it is the one that would settle everything. Inflation says that the same quantum jitter that shook the field must also have shaken space and time themselves, producing gravitational waves left over from the stretching. If you could detect those, you would not merely be confirming inflation. You would be observing gravity behaving quantum mechanically, which nobody in the history of physics has ever done. For about 11 months in 2014, a great many people believed that had just happened. On the 17th of March, 2014, a man walked up a residential path in California carrying a bottle of champagne and a piece of news, and rang a doorbell. Before we get to the door, you need to understand exactly what he thought he was carrying because it was not a routine result. The microwave background is polarized. Light picks up a preferred orientation when it scatters, and the pattern of orientations across the sky can be broken into two mathematically distinct kinds. One kind, called E-modes, looks like radial spokes and rings, and is produced abundantly by ordinary density variations in the early plasma. The other kind, called B-modes, has a handedness to it, a curl like a pattern of little pinwheels, and here is the decisive fact. On large angular scales, density variations cannot produce B-modes. It is not that they produce few, they produce none. Compressing and rarefying a fluid has no twist in it. The only thing that can leave a curl in that light at those scales is a gravitational wave passing through the plasma at the moment the light was released, stretching space one way and squeezing it the other, imprinting a twist that scalar physics is geometrically incapable of imitating. And inflation predicts those waves. The same quantum uncertainty that shook the driving field must also shake the gravitational field, which is to say space and time themselves. Those shaken modes get stretched and frozen just like the density variations, and they should still be rolling through the universe now, a background hum of gravitational waves from before the fire. So a detection would do two things at once. It would confirm inflation as decisively as anything could, and it would give us the amplitude, which would tell us the energy scale, which would tell us which of the hundreds of proposed models was the right one. And it would do a third thing that is larger than either. Lawrence Krauss and Frank Wilczek published a paper in 2014 arguing that measuring this signal would firmly establish that gravity is quantized, because the amplitude generated during inflation is proportional to Planck's constant, a factor that only appears if you have treated the gravitational field quantum mechanically. That paper is cited in the announcement we are about to discuss. Every attempt to unify gravity with quantum mechanics for the last 90 years has been hobbled by the same difficulty. Nobody has ever observed a single phenomenon that requires both. This would have been the first. The announcement came at a press conference at the Harvard-Smithsonian Center for Astrophysics. The instrument was called BZEP-2, a modest telescope at the South Pole 26 centimeters across, with 512 detectors, 3 seasons of observation from 2010 to 2012, covering 380 square degrees of unusually clean sky. The 4 principal investigators were Jamie Bock, John Kovacs, Chaolin Kuo and Clem Pryke. They reported an excess of exactly the right kind of signal, at exactly the right angular scales, inconsistent with no signal at more than 5 standard deviations, fitted by a gravitational wave amplitude of 0.2, with 0 disfavored at 7 sigma. Kovacs' line in the press release was measured. Detecting this signal, he said, is one of the most important goals in cosmology today. Pryke's was not measured at all. This has been like looking for a needle in a haystack, he said, but instead we found a crowbar. And on the same day, Stanford released a short video that went around the world. Shaolin Kuo is standing on a doorstep in Palo Alto with a bottle in his hand, talking quietly to the camera before he knocks. He explains that he is about to deliver some news to Professor Andre Linde, who is one of the founding fathers of inflation, and that their experiment at the South Pole has found what he calls the smoking gun. Linde, he says, has no idea that I'm coming. The door opens, Renata Kalosh answers it. She is Linde's wife, and a distinguished physicist in her own right, and she does not need any of it explained to her. She hugs him. Linde comes to the door. He is 70 years old. He proposed the version of this being tested 32 years earlier, in Moscow, in the middle of the night, when he woke his wife to tell her he thought he knew how the universe was created. Kuo says, "It's 5 sigma at R of 0.2. Linde says, "What? Just a second. Can you repeat it?" Kuo repeats it. Linde says, "Can you repeat it again?" And then the glasses come out, and the 4 of them are standing in a hallway in California with champagne, and Linde says, "We did not expect anybody. Renata told me it was probably some kind of delivery. Did you order anything?" And then he answers his own question. "Yeah," he says. "I ordered it 30 years ago. Finally it arrived." A little later in the same recording, he says something that I have thought about more than almost anything else in this subject. He is asked what it means, and he says, "We see the face of the Big Bang. It is an image of these gravitational waves which are purely a quantum gravity feature of what was produced in the Big Bang. And then, without being prompted, without anyone raising a doubt, while the champagne is still in his hand and the best professional moment of his life is still happening around him, he says this. If this is true, this is a moment of understanding of nature of such a magnitude that it just overwhelms. Let's just hope that it's not a trick. I always live with this feeling. What if I'm tricked? What if I believe in this just because it is beautiful? 6 months later, it was dust. Our own galaxy is full of interstellar dust grains. They are not spherical. They align themselves with the galactic magnetic field, and aligned elongated grains radiating in the microwave band produce polarized light. And polarized light from a twisted, tangled magnetic field produces, among other things, B modes. Bicep 2 had observed at a single frequency, 150 GHz, which meant they had no independent way to separate a foreground from a primordial signal. They had used the best dust models available, and those models suggested their patch of sky was unusually clean. On the 19th of September 2014, the Planck collaboration published its own map of polarized dust emission at high galactic latitudes, measured at 353 GHz, where dust dominates overwhelmingly. Extrapolating that measurement down to 150 GHz in Bicep 2's own field of view gave a predicted dust contribution of essentially the same magnitude as the entire signal. The two teams then did the honourable thing and worked together. The joint analysis was submitted on the 2nd of February 2015 and published in Physical Review Letters. Its conclusion, in the author's own words, strong evidence for dust and no statistically significant evidence for tensor modes. The upper limit on the gravitational wave amplitude came out at 0.12. Kovac's statement afterwards is a model of how to lose in public. When we first detected this signal in our data, he said, we relied on models for galactic dust emission that were available at the time. These seemed to indicate that the region of the sky chosen for our observations was relatively devoid of dust. I want to be careful about the emotional register here, because this is often told as a comedy of hubris, and I do not think it is one. There was no fraud. There was no negligence that anyone has established. There was a team using the best available foreground model in a field where the foreground model was itself a frontier problem, and a man who had waited 3 decades opening his front door to be told that his idea had been photographed, and who said out loud, on camera, before anyone challenged him, that he was afraid he was being tricked because the idea was beautiful. He was right to be afraid, and as far as I can find, there is no recorded statement from him about the retraction afterwards. The sources are simply silent. I am not going to invent one for dramatic effect. The silence is the more honest ending. Where does it stand now? The current limit comes from the successor experiments, combining data through the 2018 observing season with Planck and with the earlier microwave probe, published in 2021. The gravitational wave amplitude is less than 0.036 at 95% confidence. Klempreik's summary of what changed is the whole lesson in a sentence. The big change since 2014, he said, was to make measurements in multiple frequency bands to allow the removal of the galactic foreground. Back then they had data only at one frequency, and were relying on models and projections which turned out to be optimistic as far as the dust is concerned. There is a small, sharp irony in how they got there. The experiment that was destroyed by dust rebuilt itself as a dust instrument. Its highest frequency channel, at 220 GHz, now measures polarized galactic dust better than the satellite that corrected them did. The thing that beat them became the thing they specialize in. One of the founders of the collaboration, Brian Keating, later wrote a whole book about the episode, which I will mention and not quote from, because the title alone tells you what it cost him. It is called Losing the Nobel Prize, and that limit, which sounds like a failure, is not one. It is a blade. Because different inflationary models predict different amplitudes, and a bound of 0.036 cuts through the field. The simplest models of all, where the field's energy grows as the square of its displacement, which is the textbook version everybody learns first, are excluded. So is the version where it grows as the fourth power. So more generally is any model with a potential that curves upward as you climb it. Natural inflation, which was popular for years, is disfavored. Mark Kamienkowski's summary. Models such as natural and quadratic inflation that were popular several years ago no longer seem tenable. What survives is a narrower and more interesting set. Starobinsky's original 1980 model, the one whose author didn't know why it would be interesting. Models where the Higgs field itself does the driving, and a family of related constructions, the plateau models, the gentle ones. So we have a tilt, measured to 4 decimal places, and a gravitational wave amplitude that is smaller than we can currently see. One number in hand and one number missing, and the missing one is the one that would have shown us gravity behaving quantum mechanically. That is an honest place to be. But it is also, if you're being rigorous, a slightly uncomfortable one, because a framework that survives every attempt to pin it down by producing a slightly different version of itself is a framework you should ask hard questions about, and the hardest questions have not come from outside the field, they have come from the people who built it. In February of 2017, an article appeared in Scientific American arguing that cosmic inflation had failed to deliver on its promises and could not be tested in the ordinary way. One of the 3 authors was Paul Steinhardt. You have already heard his name tonight. He is one of the 2 people who published, in April of 1982, the version of inflation that fixed Guth's broken model and made the whole framework viable. He helped build the house, and he has spent the last 20 years telling anyone who will listen that he thinks it is unsound. I want to give this a proper hearing, not a polite nod, because the channel's usual habit of taking the fringe seriously does not really apply here. This is not the fringe. This is a founder. The argument has 3 parts. The first is about flexibility. Inflation is not a theory in the way that general relativity is a theory. It is a framework, a mechanism, plus a free function. Give me a shape for the potential the field rolls down and I will tell you what the universe looks like. But the shape is not derived from anything. It is chosen, and people have chosen hundreds of them. So when a measurement comes in, there is generally some version of inflation that fits it. And the critic's point is that a framework which can absorb a wide range of outcomes is not being confirmed as strongly as the headlines suggest when one of those outcomes shows up. The second is about infinity, and it is the sharpest of the 3. In most implementations, inflation does not stop everywhere. The field is undergoing quantum fluctuations, and in some regions those fluctuations push it back up the slope faster than the classical rolling brings it down. Those regions keep inflating, and because inflating regions grow exponentially and non-inflating regions do not, the inflating part always dominates the volume, forever. Inflation ends locally, in pockets, but globally it never ends. This is called eternal inflation, and it produces an unbounded number of pocket universes, each with its own history, and in many versions its own effective physical constants. Now try to make a prediction in that setting. To say that some observation is likely, you need to count what fraction of observers see it. But you are counting inside an infinite ensemble, and infinity does not divide cleanly. You need a rule for how to count, a prescription, what cosmologists call a measure, and there is no agreed measure. Different reasonable-looking choices give different answers, and some of them give answers that flatly contradict what we observe. This is not a complaint invented by opponents. Guth himself has written extensively about it, and has described it as the most serious unsolved problem in eternal inflation. It is a genuine open wound in the middle of the most successful framework in cosmology. The third argument is about where inflation gets its own starting conditions. To begin, you need a patch of space that is already reasonably smooth over a certain scale, with the field already positioned on the right part of its potential. Steinhardt's point is that this is itself a special condition, and that if you are willing to assume a special condition to get inflation going, you could have skipped the intermediate step and assumed a smooth flat universe directly. Roger Penrose has a version of this that is more quantitative and considerably more brutal. He estimates the improbability of the required low-entropy starting state at odds of 1 in 10 to the power of 10 to the power of 123, which is a number so large that you cannot write it out inside the observable universe, even using 1 atom per digit. His conclusion is that inflation does not remove the fine-tuning. It relocates it. The Scientific American article prompted a reply. 33 physicists signed a letter disputing the characterization and defending inflation as a productive and testable program, and the signatories included Alan Guth, Andre Linde, David Kaiser, and several Nobel laureates. They pointed out correctly that individual inflationary models are being falsified all the time. That is precisely what we watched happen in the last part. The simplest chaotic models are dead, killed by an upper limit on gravitational waves. Both sides are arguing in good faith. Neither has surrendered, and the disagreement is still live in 2026. And I think the reason it stays live is that the word falsifiable is doing 2 different jobs in the argument, and nobody separates them, so let me separate them, because once you do, the whole dispute becomes much easier to hold. There is falsifying a model, and there is falsifying a framework. A model is a specific choice. This field, this potential, this shape. Those are sharply falsifiable, and they are being killed regularly and publicly. Quadratic inflation is dead. Quartic inflation is dead. Natural inflation is on life support. Those are not soft outcomes. Those are the corpses of ideas that many careers were built on. A framework is the underlying claim that some period of accelerated expansion preceded the hot phase, and that is a much harder thing to corner because refuting one shape leaves the others standing. Which of those 2 things you have in mind determines whether you find inflation obviously scientific or obviously unfalsifiable. The defenders point at the corpses, the critics point at the survivors. Both are looking at the same field and describing it accurately. There is one more thing worth saying in the critics' favour, and it is uncomfortable for the case I've been making. Some bouncing models also produce a spectrum that is nearly scale invariant with a slight red tilt, not by accident and not by fitting after the fact. The mechanism is different, but the output is similar enough that the spectral index alone does not uniquely single inflation out. Where the 2 families genuinely part company is in the gravitational waves, inflation generically expects some, and most bounce models expect essentially none. Which is why the search that failed in 2014 is not a footnote, it is the referee. Steinhardt has also done what a serious critic should do, which is to build an alternative rather than only complain. His approach, developed with Neil Turok and later with Anna Ijaz, is a bouncing cosmology, where instead of a brief phase of stretching before the fire, the universe contracts, smooths itself out during the contraction, and rebounds. Contraction smooths for a different reason than expansion does, and it has the considerable virtue of never producing an infinite ensemble, so the measure problem simply does not arise. There are other bounce models, including one derived from loop quantum gravity, in which the singularity is replaced by a maximum density set by the quantum structure of space itself so that the universe cannot be compressed past a certain point and rebounds instead of ending. I will be honest about where these stand. They are serious, they are worked on by serious people, and none of them has yet predicted a number in advance and been right about it. And there is a structural problem they all inherit. A bounce means there was a contracting phase before, and asking where the contracting phase came from puts you back where you started. The regress does not stop, it moves. So here is the fair verdict, and I want to state it as a balance rather than as a concession, because I think both halves of it are true and important. Inflation is the only framework in this subject that made a specific quantitative prediction before the measurement existed and turned out to be right. Not almost right. Right, at 8 standard deviations, in the correct direction, by roughly the correct amount. Nothing else in the field has done that. When you weigh explanatory schemes against each other, that counts for a very great deal, and no amount of methodological unease should be allowed to obscure it. And it is also a framework whose sharpest critics are the people who wrote it, which is an unusual condition for a successful theory, and which you deserve to be told about rather than managed past. Both of those are the state of play. I would rather hand you both than pretend the first one settles the question, but underneath the whole argument, underneath inflation and its critics and the bounces and the measures, there is a flaw that nobody in this conversation has managed to get below, and it is not a matter of insufficient data or insufficient cleverness. It is stranger than that. Every version of this story assumes that there is a sequence, that things happened in an order, that there is a meaningful sense in which one state of the universe came before another. And when physicists finally sat down and tried to write a quantum description of the universe as a whole, that assumption is exactly the one that did not survive. In 1965, a man named John Wheeler found himself with 2 hours to kill between flights at Raleigh-Durham Airport in North Carolina and made a telephone call. Wheeler was one of the great physicists of the century and one of its great namers of things. He coined the term black hole. He supervised Richard Feynman. He had a habit, colleagues noted, of becoming tremendously excited about ideas. On this occasion, he telephoned Bryce DeWitt, who was down the road at the University of North Carolina at Chapel Hill, and suggested they meet at the airport during the layover. DeWitt came out to the airport with a piece of paper. On it was the Hamilton-Jacobi equation of general relativity, a reformulation that had been published shortly beforehand by Asher Paris. And DeWitt mumbled an idea. What if you did to this what Schrödinger did to the hydrogen atom? Schrödinger had taken a classical description and turned it into a quantum one by a particular substitution, replacing the square of a derivative with a second derivative. What if you simply did the same thing here, to the whole of gravity? Wheeler, in Carlo Rovelli's telling of the story, got tremendously excited and declared on the spot that the equation for quantum gravity had been found. DeWitt wrote it up and published it in 1967 in Physical Review under the title Quantum Theory of Gravity, the Canonical Theory. And the thing they had written down is now called the Wheeler-DeWitt equation, which is a name neither of them used. Wheeler called it the Einstein-Schrödinger equation. DeWitt, who never liked it, called it the Wheeler equation, or more often that damn equation. Here is what it says. On the left is an operator representing the total energy of the universe, acting on something called the wave function of the universe, which is meant to encode everything about everything. On the right is zero. That is it. The whole thing equals zero. And what that means, if you follow it through, is that the wave function of the universe does not evolve. There is no time parameter in the equation, not a time that behaves strangely, not a time that runs backwards or in circles. There is simply no variable in there for anything to change with respect to. Take the naive route to quantising the universe as a whole, and what comes out the other side is a description in which nothing happens. Try to hold this for a moment. Do not try to understand it. Just hold it. Imagine the entire universe laid out in front of you. Not as it is now, but everything. Every particle in every position it has ever occupied or will occupy. Every event, every star, your own body lying in the dark exactly where it is. All of it, present at once, in a single description. Now take away the one thing you assumed was underneath all of that. Take away the parameter that says which of these configurations comes next. Nothing moves, not because everything has stopped, which would still be a kind of happening, but because there is nothing for motion to be measured against. There is no next. The word does not apply. And yet you are lying there, and time is passing, and you can feel it passing, and the clock on the wall is quietly disagreeing with everything I have just said. Except that in this picture, the clock is not measuring anything external. The clock and you are simply correlated. There is a part of the universe whose configuration and your configuration go together, and when the hands are here you are in this state, and when the hands are there you are in that one. Nothing is flowing. The correlation is just there, all of it, complete, and from inside it, indistinguishable from a world where things happen. This is called the problem of time, and it has a large and rather beautiful technical literature. Chris Isham wrote a 125-page review of it in 1992, which is still the standard reference, and Carol Kuchar wrote a companion review in the same period that people still work from. And I should say, clearly, that the equation is not a finished object anybody is defending as correct. It has other problems besides the missing time. Written down naively, it is mathematically ill-defined. The quantities you're being asked to square are the kind of mathematical objects that cannot be squared without producing infinities. It also quietly breaks the even-handedness between space and time that was the whole point of relativity in the first place, which is an odd property for a candidate equation of quantum spacetime to have. It is not the answer. It is the first serious attempt at the question, and the reason it matters is not that it is right. The reason it matters is what happened to time when somebody tried. And I have to be careful here, because the most dramatic reading of it is disputed by the person best qualified to dispute it. Ravelli, who has spent his career on quantum gravity, argues that the absence of time does not mean a frozen world. He points out that the vanishing of the time variable is already there in the classical formulation of general relativity, before you do any quantum mechanics to it at all, so it is not some strange quantum pathology. His view is that time is not fundamental and never was, and that what we call time is relational, something that emerges when you use one part of the universe as a clock for another. His own phrasing about the equation itself is generous, disavowed by one of its fathers, ill-defined, never empirically tested, and nevertheless it has had a powerful influence on fundamental physics, and a well-deserved one. That relational picture is not just a philosophical stance, it has a concrete formulation, and it has been tested in a laboratory. Don Page and William Wouters published it in Physical Review D in June of 1983, under the title Evolution Without Evolution. Their proposal: the universe as a whole is in a stationary state, exactly as the equation says. Inside it, one subsystem serves as a clock, and it is entangled with the rest. If you condition on the clock reading a particular value, the state of everything else, relative to that reading, evolves perfectly normally. Time is not a stage the universe stands on. Time is a correlation between one part of the universe and the rest of it. And in 2014, a group in Italy actually did it. Ekaterina Moreva and colleagues built a miniature version. 2 photons in an entangled state, with the polarization of one used as a clock for the other. An observer who becomes correlated with the clock photon sees the second system evolving. An observer who stands outside and measures only the global properties of the pair can demonstrate that the whole thing is static. Both observers are correct. The system does not have a fact about whether it is changing. It has a fact about whether you are inside it. Now bring back the phrase from the beginning of the night. Georges Lemaitre in 1931 wrote that if the world began with a single quantum, the notions of space and time would altogether fail to have any meaning at the beginning, and he is remembered for calling that moment a day without yesterday. When you first heard it, a long way back in the night, it sounded like a priest's lyrical phrase for a first morning. Hear it again now. A day without yesterday is not a poetic gesture toward an early sunrise. It is a precise description of a situation in which the ordering relation itself is absent. There is no yesterday, not because yesterday was empty, but because the structure that makes yesterday a coherent idea is not there. He knew. He said so in print, in 457 words, in 1931, and then everybody named his theory after an explosion. There are 2 famous attempts to say something definite about the very beginning within this framework, and I want to place them correctly rather than dwell on them. One is the no-boundary proposal, worked out by James Hartle and Stephen Hawking in 1983. The other is Alexander Vilenkin's proposal from 1982, in which the universe tunnels into existence quantum mechanically. They are usually presented as rival origin stories. They are better understood as rival boundary conditions, rules you impose on the wave function of the universe by hand in order to pick out one solution from many. They are not derived. They are chosen, which is not a criticism of either man. It is the honest description of what that kind of work is, and that is the flaw. Not because physicists are lazy, and not because the instruments are not good enough yet. Because the question, in the form everybody asks it, contains a word that our deepest equation does not contain. Which means we're finally in a position to answer the thing we started with. Somewhere on your screen tonight there was a question, 4 words long, and it has been sitting there this whole time patiently while we went to a radio studio in London and an obscure Belgian journal and a rented house in Menlo Park and a doorstep in Palo Alto. How did nothing start? I promised you at the beginning that the true origin of the Big Bang is not what you think, and I want to pay that properly now because there are 3 answers, and they are 3 different sizes, and the only way to get them wrong is to run them together. The first answer is about the name. The origin of the Big Bang as a phrase and as a picture is a scripted talk on the BBC on the 28th of March, 1949, delivered by a man who was trying to make the idea sound ridiculous and who never accepted it for the remaining 52 years of his life. The picture in your head is not a summary of the science. It is Fred Hoyle's caricature of the science, and it has outlived him, and outlived his theory, and outlived every person who was in the room. When you imagine a blazing point in the darkness, you are not imagining what physicists think happened. You are imagining what a brilliant, wrong, generous, difficult Yorkshireman wanted you to imagine, so that you would side with him. That is a real answer, and it is completely documented, and almost nobody knows it. The second answer is about the event, and it is the one the whole night has been building toward. The origin of the Big Bang is that it is not an origin. On the leading account in physics, the hot, dense fireball we name the beginning of the universe is the closing moment of something else. Before it, there was a field, filling everything, holding still in the coldest, emptiest, darkest condition physics can describe, carrying every jewel that would ever become a star or an ocean or a hand. That field fell, and when it fell everywhere at once, because it was the same everywhere, and it poured everything it was holding into particles in something like 2 or 3 doublings of space. That pouring is what we call the Big Bang, not the beginning, the end of the stretching, the exhaust, not the engine, the ash, not the fire. Which means, and I want to say this as plainly as I can, that the thing you were taught was the first event was the last event of a story we cannot see the rest of, and I will not oversell it. Inflation is a framework, not a finished theory. Its own architects argue about whether it can be cornered. The gravitational waves that would have settled it have not been found, and the search that thought it had found them in 2014 was looking at dust in our own galaxy. All of that is true, and I have not hidden any of it from you tonight. But there is one number, 0.9649. That is the tilt. It is the measured lean in the spectrum of primordial variations, and it is what you get if a field rolled slowly down a gentle slope in an interval that finished before there was any light or heat or matter anywhere. Exact evenness would have been 1.0000. It is not one, and it is not one by 8 standard deviations, and nothing else predicted it in advance. Everything else in this episode is history or argument or an honest admission of ignorance. That is the one thing we simply know, and there is one more thing worth knowing before we go to the last answer, because it changes how this feels. The question is not closed. Right now, at the South Pole and in the Atacama and on a satellite being built in Japan, people are constructing instruments designed to look for the one thing that would settle it. The current limit on those primordial gravitational waves is 0.036. The next generation is aiming at roughly 0.001. If the signal is there above that level, they will find it in the next decade or so, and we will have watched gravity behave quantum mechanically for the first time in the history of the species, and we will know the energy scale of the thing that ran before the fire. If it is not there, the most theoretically favoured models die, and the field goes somewhere else. Either outcome is a real answer. That is what it looks like when a question is alive rather than settled, and it is worth noticing that you happen to be around for it. Which brings us to the third answer, and to your question. How did nothing start? The word doing the work in that sentence is not nothing. Everybody assumes it is nothing, and spends their energy trying to picture an absence, and gets a headache, and gives up. The word doing the work is start, because starting is something that happens inside time. To start is to have a moment where you were not, followed by a moment where you were, and the word followed is carrying the entire weight. It needs an ordering. It needs a before and an after and a direction between them. And time, on the best attempt anyone has made to describe the universe as a whole quantum mechanically, is not the stage all this is happening on. It is not underneath. Write down that equation and there is no time variable in it anywhere. What there is, on one serious reading, is correlation. A clock and a watcher, entangled, and from inside that entanglement, it looks exactly like a world where things happen, and from outside it does not look like anything at all. If that is right, then asking how nothing started is not a hard question, with an answer we have not found yet. It is a question with a tense that the universe may not have. Nothing did not start. Starting is a thing that happens to things inside a universe, and we were asking it about the universe. Georges Lemaire wrote it down in 1931 in 457 words, and he was not being lyrical and he was not being religious. He said the beginning of the world happened a little before the beginning of space and time, and he called it a day without yesterday, not a day whose yesterday was empty, a day for which the word yesterday has nothing to attach to. He put the answer in the paper, And then a man on the radio gave the whole thing a name that implies a bang, and a place, and a moment. And we have been asking the wrong question ever since, out loud, for 77 years. I do not offer that as a consolation exactly. Being told that your question has a defect in it is not the same as being given what you wanted. You wanted a first page, and I have handed you a book that opens in the middle, and a warning that the word first may not survive contact with the physics. But I have noticed over the years that this particular kind of not knowing sits differently from the ordinary kind. Not knowing what is at the bottom of the ocean is a gap. Not knowing what came before time is not a gap because there is no shape there for the missing thing to be missing from. It is more like discovering that a corridor you assumed ran on forever simply ends in a wall that is also the floor, unsettling for about a minute, and then, oddly, restful because you can stop walking. And here, right at the end, is the part I keep turning over. Hoyle was wrong about everything. Wrong about the steady state, wrong about the source counts, wrong for 50 years, wrong to the end. But he handed us 2 words as an insult, and one of them was accidentally, perfectly correct. It isn't a bang. There was no sound, and no centre, and nothing flew outward through anything. There was a field, everywhere, quite still, and then it wasn't still, and everything that has ever happened is what came out. So let that be the last thing, not a beginning, and not an explosion, and not a moment we can point to on a line. Just a number, 4 digits long, that we pulled out of the faint glow of the sky using instruments built by a species that is itself a downstream consequence of the very variations it was measuring, 0.9649. We do not know what came before. We are not sure the word before applies. We are not sure the question has the shape we have been giving it. But somebody read the tilt of the oldest light there is, and worked out the slope a field was rolling down before the universe was warm. That is the true origin of the Big Bang, and it is not what you think, and it is very much stranger, and very much quieter, and I find I sleep better knowing it. Rest well.